Hello everyone and welcome to the Undergraduate's Guide to Semiconductor Equations. This is a part 2 to my Undergraduate Guide to Semiconductor video where we will be talking about today the equations needed to tell us everything about our p-n junctions, including the carriers, the concentrations, the voltage, the depletion region width, the current, and finally the saturation current. So in order to even get to the voltage and current, we really have to do our building blocks for the p-n junction. What's the basics of the p-n junction? And those would be the carriers. We know that the electron and the hole have to move, and so they've been given a blanket term called carriers. And these carriers can be positive or negative, as the hole or the electron, but as a blanket they're denoted as n sub I. And the equation to solve them kind of looks like a lot at first, but it turns out to be kind of a plug and chug equation with a lot of constants. And the first one being the B. The B is a material dependent constant, similar to if you were trying to solve for the resistance of a resistor and you were given the resistivity of that object. Well, B is similar to that. It's dependent on the material you're using, and in most cases you'll probably be using silicon, and B will be given to you. The next one is K, which is the Boltzmann constant. I highly suggest you memorize this or you put it in your calculator or something, as it shows up quite a bit in semiconductors. It is 8.62 times 10 to the minus 5. Next, we have T, which is just temperature in Kelvin. And finally, we have EG, which is the band gap energy. In my last video, I mentioned jumping the band gap was similar to jumping a river. Well, the energy required to jump that river is given by this E sub G right here. Finally, well, not finally, but next in our building blocks are the concentration variables. The concentration of holes or positive carriers is denoted by P, and the concentration of the electrons or the negative carriers is given by N. Together they make N sub I, which is our blanket term for carriers, concentration squared. And then moving on for concentration, we have to ask ourselves the question, how much dopant are we putting in the silicon wafer? And if we want to know everything about our p-n junction, we have to know exactly how much did we put in on the N side, how much did we put on the P side. Well, on the N side, we put in elements that have more electrons than silicon, and so those are considered donors because they donate the extra electron. And the ones that have less are considered acceptors because they accept the extra electron, because they have extra holes than silicon does itself. So the acceptor concentration is given by N sub A for acceptor, and the donor's concentration is given by N sub D. With these finally all together, we can move on to the voltage. Now, above I have a diagram of a reverse bias p-n junction, but we'll get to the reverse bias in a little bit. Before we even look at any bias, we can solve for the built-in voltage just by given this constant V sub t, which is most of the time 0.25 millivolts, but it depends on the question and it will be given to you. And you multiply this by the natural log of n sub a, n sub d, what we just learned, all divided by the carrier concentration squared. Now that you have your built-in voltage, so you don't even look at the circuit yet and you can tell the built-in voltage, we need to move on to the width of our depletion region, a very important characteristic in p-n junctions. It has square root in it, which means it's relatively going to be a small number. And it starts off with 2 times epsilon sub s. Now this is the permittivity of the substance you're using, and just like if in physics for electronics, it's the same type of permittivity you learn there, divided by the charge of an electron times 1 over big N sub A plus 1 over big N sub D. So we have our dopant concentrations and multiplied, and here's the most important part of the width equation in my opinion. This is the voltage area. This is the built-in voltage we just solved for, and now this is V sub R. And if we look up here, V sub R is what makes this what makes this in reverse bias. If you look at it, it piles up more electrons, it piles up more holes, so therefore the gap is way harder to traverse because it's way bigger, and it's way bigger because you add the voltages together. So the higher the voltage, the larger the gap is, and the harder it is to jump the gap. Now if we look under it, I have a circuit of a forward bias, and the forward bias p-n junction, and the equation is strikingly similar, except instead of adding the voltages, you now subtract the voltages. Because if this voltage is making everything flow nicely, there's no traffic whatsoever, and this width eventually would go to 0 because this usually acts like a short in forward bias. So now with the width out of the way, we can move on to the final, probably more complicated aspect of a p-n junction, and that would be the current through the p-n junction. The current is given by the saturation current times e to the voltage divided by that voltage constant we used earlier, minus 1. Now, saturation current is given by the area, so it's essential that you know the cross-sectional area that your current's going through. Once again, it will more than likely be given to you, multiplied by the charge of an electron times the carrier concentration squared. And if we look here, we have a couple of new faces here with this dp, lp, dn, ln, but we do recognize the nd and na. Well, these lp and ln are the diffusion lengths, and these dp and dn are the diffusion constant. How well will a hole diffuse in the n side, and how well will an electron diffuse in the hole side? And these are just characteristics, again, given by either your dopant or the material that you are doping, and they will be given in making this another plug and chug type of equation. Thank you so much for watching, and I'll see you next time when we cover the MOSFET.